So this element is chlorine. Chlorine has atomic number 17, so that means it has 17 protons. And to be neutral electrically, it needs 17 electrons because protons are positive charged, electrons are negatively charged, so that would balance out to 0. The other thing I wanted to point out before we start is that we can figure out the valence shell configuration by looking at the periodic table placement of chlorine. So chlorine is in group 7, so we know 7A, so we know that it has 7 valence electrons. So keep that in mind. And then we're filling up the third, our chlorine is on the third row or third period. So anything in period 3 is working on filling up the third shell. So in group A elements, we have shell 3 is designated by being in period 3. So the valence shell is the third shell because it's in period 3, and there's 7 valence electrons because it's in group 7. All right, so let's fill this up. So we have in shell 1 2 electrons, and then in the s orbital, and then in shell 2 we have 2 electrons in the s, and then we have 3 in the p, px, py, and pz. We do them individually before we double them up because of Hund's rule. And then we have the third shell has 2 in the s, and then p gives 3, and then we double them up, and that's 5. Okay, so we have a configuration of 1s2, 2s2, 2p6, 3s2, 3p5. And then we're done. So all these other orbitals are not filled, and so they just are going to go away because this is our configuration. All right, so that's the electronic configuration of chlorine. So its valence shell is 3 because it's in the third shell, and there are 7 valence electrons. And the configuration of the valence shell would be 3s2, 3p5. All right. This one is krypton, atomic number 36, which means that we will have to have 36 electrons to balance out the positive 36 protons. And so we have 36 electrons to deal with. And so we'll start filling them up. So we'll put 2 in the 1s, and then we'll get 2 in the 2s, and then the 2p, we put 1 in each one via Hund's rule, and then we can double them up. That's 2p6, and then 3s2, and then 3p6, and then 4s2, and then we need to add some more shells, but based on that zigzag line for the electron orbital filling that we have in the lab, we're going to add a 3D next. So we go back to the third level, and I'll put it kind of in between because it overlaps with the S4S. So we'll put 5 electrons in it. And then we need a P for the fourth one. So we're back to the fourth level. Okay, so we have for a valence shell is the fourth one, is number 4. And our configuration will be 4s2, 4p6. And so even though this one is without electron, or with 8 electrons, that just means that it's stable and it doesn't react, and that's what we see in real life. It rarely reacts with anything because this already has this 8 electrons or its octet. So they're trying to get 8 electrons in the valence shell, which is the fourth one, and those are full. Okay, and so we can do the shortcut method to figure out what the valence shell is. It's in period 4 is where krypton is in the periodic table, so that means this valence shell is the fourth valence shell, fourth energy level. And then the configuration for the group tells us that there's 8 electrons, so because it's in group 8. And so the valence shell will have a configuration of 4s2 4p6. All right, so our overall configuration versus our electron valence shell configuration. So the overall configuration is all of these shells in the order that's dictated. And so it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d10, and then back to 4p6. And then just the valence shell will be 4s2, 4p6. And then that one is complete. And so keep in mind that the shells are the distance from the nucleus. So here's the nucleus down here. The larger the shell, the further out they are, because they have more energy. The electrons are moving more energetically, and then they can swing further from the nucleus. All right, that should be it. Thank you.